Hello all, I'm back with another video, also in a past paper, and this time is Unit 2, and I think this is the first time I am uploading any material related to Unit 2. The reason why I'm doing a Unit 2 paper before uploading any lessons on Unit 2 is because I figured that it's gonna help my mind get going, and also, going through past papers helps you identify what's important and what's not in the material. And I'd recommend the same to you, even though, okay, I mean, you guys are students, so I mean, for me, even if you give me some random physics material, it's just a matter of time to read it and figure out what's important and what's not, because I have a lot of physics training due to my studies. But if you're a high school student, that's harder, but not impossible, right? So I think it's good to take a look at the past paper before you even start your first class on Unit 2, Unit 1, Unit 3, Unit 4, whatever. So anyway, since we went through the Unit 1 January 2024 paper, we will now go over the Unit 2 January 2024 paper, okay? So let's dive in. These papers are also 1 hour and 30 minutes long, so you have to time yourself. I keep repeating the same things, but the rule of thumb that I have is that if a question awards 1 mark, it means that it should take you 1 minute. If it awards 15 marks, 15 minutes, and so on and so forth. I mean, you don't have to be religious about it, but it's, it's good to have it in the back of your mind. In case I hesitate a little bit about an answer, this is because I haven't seen this material and my notes in 2 years, but let's do it. So question 1, a ray of light in air is incident on a glass surface. The angle of incidence is less than the critical angle. Which of the following describes what happens to the ray of light? Partially reflected and partially transmitted. This is probably the correct answer, right? So yes, A. But let's read the other ones. Refracted away from the normal. Let me see. In air is incident on glass. So this is the glass and this is the air. No, this is what's gonna happen, right? So totally internally reflected, no, and transmitted along the normal. No, because it has to be vertical, right? So let's move on to question 2. There is an increase in the intensity of light incident on a light-dependent resistor LDR. This causes a change in the number of conduction electrons and a change in the resistance of the LDR. Which row of the table describes these changes? So if light is incident on a light-dependent resistor, this means that we will have an increase in the conduction electrons, right? Because they will absorb energy from light, correct? And therefore, the resistance will decrease, right? Because there will be more charge carriers, right? So the answer is C. Okay. Let's move on to question 3. An electron has a de Broglie wavelength of 3.5 times 10 to the minus 10 meters. Which of the following expressions gives the velocity of the electron in meters per second? Okay, let's start with Prince de Broglie's wavelength for the electron. Since we are dealing with momentum, we can write m times v for the momentum, right? And just solve for v. So we have h over the mass of the electron times lambda. Okay, so we need 6 times 63 times 10 to the minus 34 joules times seconds in the numerator. So only options A and B offer that. And then the mass of the electron in the denominator is 9.11 times 10 to the negative 31. And you can see immediately that the correct answer is A. Question 4, which of the following describes a change in energy of 1 electron volt? So literally the definition is that since the energy is Q times V, if we have one electron passing through a potential difference of 1 volt, then we get an energy of 1 electron volt. Okay, so the correct answer is by definition C, right? An electron is accelerated across a potential difference of 1 volt. Okay, A and B are automatically wrong. A charge of 1 coulomb, that's too much. 1 coulomb contains 1.6 times 10 to the 19 electrons. Okay, so that's a really large charge. And then D, there is a current. What does current have to do with all this? So that's wrong. So C is the correct answer. So we can see this with the process of elimination as well, even if you don't know the answer at all. Okay, question 5 is a tricky one. It tricked me. Okay, so the diagram shows a 1.5 volt cell in a circuit with 2 resistors, right? The cell has negligible internal resistance, and okay, we see the circuit, the switch is closed. What is the reading on the voltmeter? Okay, we are tempted to write immediately that, we can write that we have a resistance of 10 ohms, and then the total resistance in the circuit is 10 plus 5 ohms, right? Ohms cancel times 1.5 volts, which means this is equal to 2/3 times 1.5 is 1.5 volts is 3/2, right? So 3 cancels, so 1 volt, oops, so 1 volt, and the answer is C, right? This is what everybody will be inclined to do, right? But that's wrong, okay? So the mark scheme says that the answer is D, okay? Let's go see why. It took me a while to convince myself. So don't worry if you got this wrong, or if the intuition is, if your intuition fools you. It fooled me as well. So what's going on here? If we close the switch, okay, we are effectively having 2 resistances over here in parallel, right? Let's call this R1, and let's call this R2. But then you're going to say, Valentino, what the hell is R1? Like there is no resistance there. You can consider the resistance of the wire as 0 resistance, right? So you can think of R1 as being 0 and R2 as being 5 ohms, right? And then we can say 1 over R total is 1 over R1 plus 1 over R2. Okay, I know it's crazy, but let me show you something. 1 over R1 is 1 over 0 plus 1 over 5. So 1 over R total is practically 1 over 0 is infinity. If someone is a mathematician here, they will faint if they see this. I'm sorry, but in physics you can say that 1 over 0 is infinity, okay? Positive infinity. All right, which means, okay, that the total resistance of this part of the circuit is 0, right? Which means that we are effectively removing this loop from the circuit when we close the switch. I know it sounds crazy. And therefore, across the 10 ohm resistor, we're going to have 1.5 volts because that's the battery we have in the circuit, right? Crazy, but this is the answer, okay? Let's go to question 6. A uniform wire is attached to a meter rule. The wire is connected in a circuit as shown. Okay, we have a meter rule. Okay, the distance D between the connections to the voltmeter is increased. The reading V on the voltmeter changes. Which graph shows the relationship between V and D? Okay, this involves, okay, we need a little bit of thinking here. So V, the voltage, is current times resistance, right? So voltage is current times a resistance of this sort, which depends on the length along the wire. The resistance of a wire, I'm sorry, can be written as rho over the cross-sectional area times D. Okay, so if d is 0, then v is 0. If d is d, I mean the length of the wire, maybe we can write this as x so I don't confuse you. Okay, times x. Okay, so if x is 0, v is 0. If x is d, v is v max. Okay, and what kind of formula is this? It's a linear relationship, right? Let's go look at these graphs. So this cannot be it, right? Because the voltage decreases as we increase d, but we want it to increase. Okay. This one does not start from 0, this one does not start from 0, so the only correct answer is C. I hope this makes sense, okay? So you see that in this kind of problem, sometimes you have to get creative. So, 7. A microphone is attached to an oscilloscope. The microphone detects a sound. The trace displayed on the oscilloscope screen is shown. Okay. Okay. One horizontal division represents a time of 0.015 seconds. Okay. Which of the following expressions gives the frequency of the sound in hertz? Okay, so first of all, let's find the period. So how many squares make a period? 1, 2, 3, 4, right? From here to here. So 4 squares. So 4 times 0.015. Thus, the frequency is 1 over the period. So it's 1 over that, 1 over 4 times 0.015. And the answer is D. Okay? This was easier than the previous ones. 8. At a distance d from a point source of light, the light intensity is I. Which of the following expressions gives the light intensity at a distance 2d from the source? Okay, so let's say that the source has some power P, okay? So, I mean, the situation is, okay, maybe we have a light source with power P, and here you are at a distance d. Actually, I'm going to run out of screen, okay? When I become a rich YouTuber, I'm going to buy a larger screen, but for now, no. So, this is d. Okay, the intensity here is P over 4 P d squared, and then we add another d, okay, and we want the intensity there, which is going to be P over 4 pi and then d over 2 squared. Therefore, no, 2d, sorry, 2d squared is going to make 4d squared, right? Therefore, this is going to be I over 4, okay? Sorry for my handwriting. I promised to improve my handwriting, and sometimes I slide back to old habits. Okay, B is the correct answer. Question 9. Two polarizing filters X and Y are arranged between a light source and an observer as shown. The intensity of light reaching the observer is maximum, okay? The observer rotates filter X, the observer then rotates filter Y, so that the intensity of light is a maximum again. Which of the table shows possible angles of rotation for the filters? So, okay, so the intensity of light reaching the observer is a maximum. The observer rotates filter X, the observer then rotates filter Y, so that the intensity of light is maximum again. Okay, so for these to occur, the difference between the angle of rotation, okay, for example, in option A, the difference between the angle of rotation of X and Y is 90, right? Therefore, you're going to have a minimum. Same goes for option B and option D. But in option C, The difference between the angles is 180 degrees, which means that we are practically bringing back the maximum that we had in the beginning, right? So the answer is C, okay? Do I have a better way of explaining it? So to have a maximum, it's like maybe the orientation is like this, I mean, right? So if you rotate, and this is X and this is Y, and let's say you rotate X by 270, so you practically make it, this is not a good example. No, I can't reproduce it, but I hope this makes sense. So the answer is due to the fact that the angle between these two, the difference of the angles between these two is 180. So C is the correct answer. Let's move on. Question 10. In an atom, an electron drops from energy level E2 to energy level E1 as shown. A photon of wavelength lambda is emitted. Which of the following expressions gives the energy E2? Okay, so E2 minus E1 gives you a photon of wavelength lambda. Therefore, the energy is going to be equal to H times C over lambda, right? So we need E2. E2 is just E1 then plus HC over lambda. So what's the correct answer? B. Okay. And this is what we call delta E in your book. All right, let's move on to question 11 now. Okay, this is a 2-mark question, therefore we expect it to be simple and quick, right? 2 minutes. So let's see. Light from a laser is incident at 90 degrees to a reflective surface as shown. Okay. A. Light from the laser is coherent. State what is meant by coherent. So my answer says that there is a constant phase difference between the photons, I guess, of the source. Therefore, that's why you see a very intense bright light from lasers. But I want to check the mark scheme to make sure that I am giving you the correct answer. So in the mark scheme, they say that there is a constant phase relationship or difference. Okay, so is it the same? So let's move on. B. State why a standing waveform, that's a typo there actually, okay, between the laser and the reflective. Sorry, it's not a typo. I'm sorry, I am reading it wrong. So B, state why a standing wave forms between the laser and the reflective surface. So this is interference, guys, right? So because the reflected light interferes with the incident light, we have superposition and a standing wave is formed. Okay. Question 12. A circuit contains a filament bulb. When the potential difference across the filament is 8.9 volts, the resistance of the filament is 7.5 ohms. Calculate the time taken for a charge of 5 coulombs to flow past the point in the filament. Okay, so let's find the current in the circuit. So the current is simply equal to the voltage over the resistance. So 8.9 volts, right, over 7.5 yields 1.19 amps. But I current is charge per time, right? So the time is given by Q over I, okay? So we need 5 coulombs to pass through this wire that has a current of 1.90. Therefore, it will need 4.21 seconds, okay? Let me quickly check the mark scheme. Yes, okay, it's correct. Let's move on to question 13. A glass is filled with transparent hydrobeads. The glass is then half filled with water. The beads under the surface of the water seem to disappear, as shown. They do disappear. Okay, I didn't realize that it's filled with hydrobeads. Okay. The refractive index of the hydrobeads is very similar to the refractive index of water. Explain why the hydrobeads are difficult to see when surrounded by water. Okay, so the index of refraction, I guess, is what makes the difference. So basically, the index of refraction of the beads is similar to the index of refraction of water so there is a very small change in the velocity of light in this medium, right? In the velocity of light, hence little to no refraction. Okay, let's move on. B, a ray of light in air is incident on a damaged hydrobead. The diagram shows the ray until it is incident on the damaged surface at position X. The refractive index of the material of the hydrobead is 1.38. Calculate the angle of refraction R. So this is the angle we need to find. Therefore, we can use Snell's law, right? So the index of refraction of air times sine of 42, times sine of 42 is equal to the index of refraction of the beads times sine R. Therefore, sine R is 0.67 over 1.38 because the index of refraction of air is 1. So R is just 29 degrees. Part 2. Complete the diagram to show what happens to the ray at position X. Your answer should include a calculation. So, okay, we have to do the Snell's law one more time. So let's see. Now the incident angle is 50 and we are into the beads. Therefore, we have the index of refraction of the beads times sine of 50 should be equal to the index of refraction of air times sine of, now I'm a little bit confused. Okay, so the ray should go something like that, right? So let's call this angle R double prime. So sine of R double prime. So sine of R double prime is 1.06, which is larger than 1. Therefore, what happens? Total internal reflection, right? So we have, let's write it, total internal reflection so let me think. So we can find the critical angle. Do we need it though? So okay, for total internal reflection, we will have, okay, let me erase this. I haven't seen these things in a while, guys, so that's why I'm a little bit confused right now. But yeah, this is what's gonna happen. So this is gonna be 50 degrees. Okay, we can also calculate the critical angle if we want. I mean, the answer is done right now. Okay, let me see what they say in the mark scheme. Okay, no, you don't really have to calculate the critical angle. So, but I'm gonna, okay, so this is the first way of solving the problem. The second way is to find the critical angle, but you don't know. Okay, let me see. You can also calculate the critical angle for this problem, but I think that's not the right approach. I like this approach, so I'm gonna leave it here and move on. Okay, so I'm trying to say that if you calculate the critical angle, you will find that it's 46.5 degrees, say, which is less than 50 degrees. Therefore, you do have total internal reflection. This is the idea. But okay, I mean, I prefer this answer. So we will move on. Question 14. A student investigated the EMF and internal resistance of a battery. The student connected a high resistance voltmeter across the battery. The battery was not connected to any other components. Explain why the reading on the voltmeter gave the EMF of the battery. So because actually let me move this up here, okay, to make space. So because there is no current, in the battery, okay, there was no potential difference. Across the internal resistance. Okay, so therefore we don't have any drop in the voltage, in the EMF. Okay, part B. The student investigated how the potential difference V across the battery varied with the current I in the battery. Draw a circuit diagram for this investigation. Okay, so first of all, let's start with the battery. Let's draw a battery pack as they do at the A levels for some reason. If you know the reason, let me know. I mean, usually you just draw a battery, but for some reason they prefer a battery pack. Okay. Okay, let's close the circuit. Okay, let's use, we need a voltmeter, right, across the battery to measure the voltage. And we need to vary the current. Therefore, we also need an ammeter to measure the current and a variable resistor. So we have current in this circuit, right? That we can also vary. Okay. And this is our pretty circuit. Okay. The voltmeter is not fully connected. Okay, great. Part C now. And part 1. The student plotted her results on a graph as shown. determine the nth and internal resistance of the battery. So the voltage that we actually measure is equal to the nth minus the voltage drop across the internal resistance, and R, lowercase r, is the internal resistance, okay? So, so when you plot this, so since we do have the plot of voltage versus current, this is of the form of y equals some constant c plus mx. M is the gradient, okay, and it's negative here, so we can immediately read off the mth. So the mth is 8.8 volts. So mth is 8.8 volts, and this is for zero current, right? And to find the internal resistance, we need to find the gradient of this graph. So the gradient is equal to, we can take these 2 points. Okay, let's take these 2 points, this one and this one. Okay, so in the numerator we have 8.8 minus 4, which is the voltage, and then 0 minus what's the current here? Let me see, 2.1. Yeah, 2.1. So the gradient is minus 2.29. So R is 2.29 ohms, not too large, which makes sense. Okay. Anything else here? No. Okay, part 2. Explain why there is a maximum current that can be supplied by the battery. Okay, we can start again from this formula, this relationship, that the voltage across the battery pack, this one, okay, is equal to the nth of the battery minus the current times the internal resistance. So you can say that as I increases, it will eventually be the case that I times R is equal to the nth, right? Because the current cannot keep increasing forever, right? At some point it will equal the nth, okay? At that point, V is going to become 0. So with no potential difference, no current, the current can no longer increase, okay? So at that point, V equals 0, or nth is equal to IR. So therefore, so this is I, therefore the current can no longer increase. Okay, what do they show here? The current goes, I mean, they kind of show this case here, right? Because the voltage goes to 0 at when the current is 3 point something, 3 point, say 8 amps. So, all right, I'm talking about this point, by the way. Okay. Question 15. The photograph shows a musical instrument called a harp or arp. I don't know how it's pronounced in English, because this is a Greek word, and this is, I think, the instrument of choice for god Apollo. So we like Apollo. He was a cool god. I mean, the sun god or something like that. The brother of Artemis, for those of you who are into mythology. All right, so when a harp string is plucked, transverse waves travel along the string, forming a standing wave. State what is meant by a transverse wave. So transverse means that the oscillations the oscillations are perpendicular to the direction of wave travel. All right. B. The diagram represents one string of the ARP. The string is fixed at both ends. The string is made to vibrate at its lowest frequency. Add to the diagram to show the stationary wave on the string. You should label any nodes and antinodes. Okay, lowest frequency means that, actually let me use a different color. I just discovered this feature of good nodes. So if I draw this and hold it, it makes a really nice curve, right? You see? So I have to hold it for a few seconds and it does that. So in the lowest possible frequency, we have two nodes at the ends and an antinode in the middle. Let's move on. One string produces, this is C, one string produces sound with a frequency of 196 Hertz. The wavelength of the wave on the string is 0.72 meters. The tension in the string is 41 newtons. This string breaks and needs replacing with a new string. The table shows the mass of 4 new strings A, B, C, and D. Each new string has a length of 1.5 meters. Okay. The new string is cut to the same length as the broken string, and it's placed under the same tension. Deduce which new string A, B, C, or D should be used to replace the broken string. Okay, this is a little bit of a complicated problem, but okay, so we can actually, let me see if they have it in the back of the paper before I say anything. I want to check something. So if you go in the back of the paper in Unit 2, okay, particle waves, do they have they do, yes. Okay, this is what we will use. The wave speed is equal to the frequency times lambda. The speed of a transverse wave is equal to the square root of the tension over mu, and mu is mass per unit length. So we will use these two formulas and I will show you how. So where were we? Here. Okay, so lambda times F is equal to the square root of the tension over mu, right? So let's take the square of this for both sides to get rid of the square root. So mu is nothing but the tension over lambda squared times frequency squared, but mu is mass per unit length, and this is equal to the same quantity we had before. So the mass is equal to the tension times the length over the wavelength squared, frequency squared. Okay, did I mess up something? I didn't. Okay, 41 newtons is the tension. We have 1.5 meters for the length. Lambda is the wavelength, 0.72. Don't forget to square, and 196 hertz for the frequency squared again. So this works out to 3.1 times 10 to the negative 3 kilograms, which is 3.1 grams. And the correct answer is B. Okay, so use string B. And this was question 15. Okay, question 16. A metal rod on top of a church may have been the world's first lightning conductor. The metal rod is connected to the ground by a steel cable as shown. Okay. When lightning strikes, charge is transferred to the metal rod and is conducted to the ground through the steel cable. The steel cable has a diameter of 12 millimeters. The total resistance of the cable is 0.078 ohms. Calculate the total length of the cable and they give you the resistivity of steel, which is also written as rho, as 1.4 times 10 to the negative 7 ohms times meters. Okay, so this is straightforward. The resistance is equal to the resistivity times the length of the wire over the cross-sectional area of the wire. So we need to find the length. So the length is equal to the area equal to the cross-sectional area, times the resistance over resistivity. Okay, the area is pi times d squared over 4, right? Times r over the resistivity. And let's plug in numbers now. So 3.14 times d squared, diameter is 12, times 10 to the negative 3 squared. And don't forget to convert millimeters to meters, grams to kilograms, and so on and so forth, right? The resistance is 0.078 ohms. And then we have 4 times the resistivity, 4 times 1.4 times 10 to the negative 7. So this is 63 meters, and that's it. And it does make sense, right? 63 meters. This is a tall church, okay? But it makes sense, right? I mean, you can have buildings that are that tall in real world. I mean, if you found the answer to be 6,000 meters, even the Burj Khalifa is not that tall. So yeah. Part B, during a lightning strike, there was a potential difference of 1.5 times 10 to the 8 volts between the metal rod and the ground. This potential difference caused a current of 1.2 times 10 to the 4 amps in the cable for a time of 70 microseconds. Calculate the work done as the charge is conducted to the ground. Okay, so this is a little bit complicated, but not that complicated. So let me think. Actually, let me check the mark scheme to see what kind of formulas they give you, and then I will provide the answer that I have here in my notes. Okay, they give you this formula. So the work done is voltage times charge. Okay, so this is what I will use, and this is what I have in my notes. So I wanted to double check that this makes sense. So okay, part B. During a lightning strike, there was a potential difference of 1.5 times 10 to the 8 volts between the metal rod and the ground. This potential difference caused a current of 1.2 times 10 to the 4 amps in the cable for a time of 70 microseconds. Calculate the work done as the charge is conducted to the ground. Okay, this is easier than it seems because the work done can simply be calculated by the charge times the voltage. How much charge did we have? We can use the definition that the current is charge per time. And if we combine these two, we find that the work done is equal to the current times the time times the voltage. Okay, so this is a simple multiplication. The current is 1.2 times 10 to the 4 amps. The time is, let me move down here, 70 microseconds, so 70 times 10 to the minus 6. And the voltage is 1.5 times 10 to the 8. If you multiply all this together, you get 126 times 10 to the 6 joules. That's a really large energy, okay? Which is what you expect, right? It's lightning. So The steel cable is replaced with a copper cable. The copper cable has the same length and diameter as the steel cable. During the thunderstorm, the potential difference between the metal rod and the ground is the same for the copper cable as it was for the steel cable. Copper has a lower resistivity than steel. There is a greater number of conduction electrons per unit volume in copper than in steel. A student states that the drift velocities of electrons will be the same in both cables. Assess the student's statement. Okay, we can say that since copper has a lower resistance, right? Because resistance is resistivity times length over cross-sectional area. So the length and cross-sectional area are the same. Cross-sectional area, are the same for the cable. For the steel and copper cables. Then the only thing that changes is the resistivity, and with copper having lower resistivity, it means that it has lower resistance. Okay, so since copper has a lower resistance, the current will be higher, okay, in copper than in steel, okay, but current is equal to N times Q times V times cross-sectional area. So the drift velocity is equal to the current over charge times N times cross-sectional area. So let me see. So we can't tell whether the student is correct or not. Oops. Whether the student is correct or not due to the ratio I over N, because we don't know the exact numbers for the current or the charge carrier, so we cannot tell whether the student is right or wrong. Let me check the mark scheme, because I got suspicious about the answers that I have here in my notes from 2 years ago, so let me see. So in the mark scheme, they say the copper cable has a lower resistance. With the same potential difference, there is a greater current in the copper cable. Okay, this is what we said, right? Okay. Since I is NQVA, it is not possible to say whether the student is correct or not. Okay, so yeah, that works. And okay, let me check one more thing. NQVA equals I. Let me see something. Okay. So I'm double guessing myself, but no, that's correct, because the key here is this ratio, right, of the current over the number of charge carriers in these wires. We don't know the exact number for the current or the charge carriers, therefore we cannot tell. He's probably correct, but we cannot tell. So let's move on. So to question 17. Boats can shelter from waves on the sea in a harbor. The diagram shows a harbor where boats can enter and leave through the gaps in the harbor wall. Okay, so these are the gaps. Okay, it looks like a double slit experiment. So waves on the sea are diffracted as they pass through the gaps in the harbor wall. Describe how Huygens construction can be used to predict to predict the shape of diffracted wave fronts. So each point, this is the Huygens construction, so is each point of the wavefront okay, can be treated as a source of secondary waves. These waves interfere and the resulting waves can predict the shape. So you pretty much take each point as a secondary wave like that, and then you connect the wavefronts, and then you take those points there and you do a Huygens construction again, and so on and so forth. You don't have to draw anything in this answer. Let me check with the mark scheme. Yes, they don't require you to sketch a diagram, so that's good. In the mark scheme, they say each point on a wavefront is treated as a source of secondary wavelets. These further wavelets interfere, superpose, and the resulting waves predict the shape. Okay, so exactly what we said. Part B. This is a long writing problem. The wavefronts in the sea arrive parallel to the harbor wall. The wavelength of the waves varies as the weather varies. There are identical boats at two positions A and B in the harbor as shown. As the wavelength of the waves varies, the boat at position A always oscillates with a large amplitude. The boat at position B sometimes oscillates with a large amplitude and sometimes oscillates with a very small amplitude. Wait, let me read it again. The boat at position B sometimes oscillates with a large amplitude and sometimes oscillates with a very small amplitude. Okay, what's the question? Explain why the boats oscillate as described. Okay, so first of all, the waves diffract at the gaps. Okay, so the waves diffract at the gaps. Okay, waves from each gap interfere. Okay, at position A, the path difference between the two waves from the gaps, or we can just say position A, the path difference between the two waves is an integer multiple of lambda. Okay, so 0, 1 lambda, 2 lambda, and so on. Okay, so we get constructive interference, and the boat oscillates with a large amplitude. Okay, I'm going to call it A. At position B, okay, the path difference varies with lambda. Okay, if we get a path difference of lambda, 2 lambda, etc., we get constructive interference. Okay, interference. And if we get a path difference of lambda over 2, 3 lambda over 2, etc., we get destructive interference. And that's the answer. Okay, let's move on. I hope it's clear. So at A we get constructive interference. It oscillates with a large amplitude. At B, things kind of vary. So sometimes the path difference is lambda over 2, therefore no large amplitude oscillation. But sometimes it's lambda, so we get a large oscillation and so on. So it's not steady. The phase difference is not steady. Okay, and this happens in real life. Okay. I wonder if you pay a lower rent at the harbor if you park your boat at B, or if they reserve spots where there is no oscillation, so your boat is safe during winter or something. I don't know. Let me know your thoughts about this in the comments. So, question 18. The resistance of a particular thermistor varies with temperature as shown. Okay. A student connected the thermistor in series with a battery and a resistor as shown. The resistor was made from a long length of wire. Okay. At a temperature of 45 degrees, the resistance of the thermistor was 4 times the resistance of the resistor. Okay. The power P dissipated in the resistor was 0.38 watts. Derive the equation P equals V squared over R. Okay, so power is I times V, current times voltage. Voltage is I times R from Ohm's law. If we combine, we get P equals to V over R times another V, so V squared over R. Okay, I guess this is 2 marks given away for free, right? Because I bet you can read these equations off the back of the paper. Okay, let me erase a few things here because it's a mess. I created a mess. Okay, so let's see. So these 2 equations is what we use. Okay, so this is free lunch, guys. Okay, don't lose marks like that. It's easy, I think. So wait, I promise that as a physics teacher, professor, whatever, I would never use the word easy and physics together. So, but anyway, I mean, you can figure this out. So, part 2, determine the potential difference across the battery. Okay, so first of all, let's go at the graph and find. So at 45 degrees, so this is 50, so 42, 44, 46. Okay, so here. Okay, so I hope you can see this. So at 45 degrees, the resistance of the thermistor is 34 ohms. Okay, so the resistance of the thermistor, it is stated that is 4 times the other resistance, this one. Okay, so the resistance is simply 8.5 ohms. So the total resistance, since they are in series, is 42.5 ohms. I added those two. So the voltage across the resistance is equal to the square root, I'm using this formula, okay? The square root of power times R. So the power dissipated is, they say 0.38, and the resistance is 8.5. Okay, so the voltage is 1.8 volts. Okay, so now the voltage across the resistance R is 8.5 ohms over the total resistance in the circuit, which is 42.5, times the voltage of the battery. So the voltage of the battery is 42.5 times 1.8 over 8.5, or 9 volts. Is this correct? Let me check the mark scheme because sometimes I get insecure. I'm a human being as well, guys. So yes, okay, they say 9.1 volts. Okay, no big deal. So part B, explain why the resistance of a thermistor decreases as the temperature increases. So let's see. So when the temperature increases, the we have an increase. We have an increase in the number of conduction electrons. Okay, so current increases, so the current increases. Okay, thus the resistance, which is voltage over current, decreases. Okay, and part 3, the student increased the temperature of both the wire resistor and the thermistor from 80 degrees Celsius to 90 degrees Celsius. Explain why the current in the circuit decreased. So an increase in T, the temperature, leads to a higher, maybe we can write it to, leads to an increase, okay, it's better this way, leads to an increase in the number of atom vibrations in the wire. Okay, so that's the first observation. Remember that you have a wire, and the wire consists of atoms in a lattice, and these things vibrate back and forth. Okay, so if we increase the temperature, they vibrate more. Okay, so that's the idea. Okay, so this means that the resistance of the wire increases. So the resistance of the wire increases. Okay, due to the increased number of collisions. Okay, collisions in the wire. All right, Since current decreases, okay, the total resistance in the circuit increases, okay, which means this is a long problem, sorry guys, which means that despite the reduction in R of the thermistor, the increase in R is larger. So we kind of have competing things going on here. So the resistance of the wire increases, and even though the resistance of the thermistor decreases, okay, we still have a larger increase in the total resistance due to the increased resistance of the wire. Okay, I hope this makes sense. And 19, I think, is the last problem. Okay, that's good. Solar cells are made from semiconductor materials. Okay, one type of solar cell has two layers of semiconducting material, layer 1 and layer 2. Photons of light are incident on the solar cell as shown. The minimum energy to release an electron from a semiconductor layer is the work function. The work function of layer 1 is 1.86 electron volts. Calculate the minimum frequency of light needed to release an electron from layer 1. So energy is H times the frequency. So the frequency is energy over H, and they give us the energy as 1.86 electron volts, and 1 electron volt is 1.6 times 10 to the negative 19 joules. And then H is 6.63 times 10 to the negative 34. And this results in 4.49 times 10 to the 14 hertz. And that's the answer. B. Light from the sun is incident on the solar cell. The intensity of the incident light is constant. Layer 1 has a greater work function than layer 2. Photons not absorbed by layer 1 are transmitted to layer 2. Okay, layer 1 is removed from the solar cell so that all photons now reach layer 2. Explain how removing layer 1 affects the rate at which electrons are released in the solar cell. You should assume that each layer absorbs all photons with a frequency greater than the minimum frequency for that layer. Okay, so they tell us that the work function for material 1 is larger than the work function for material 2. They also say that photons not absorbed in layer 1, okay, are transmitted to layer 2. Okay, what else do we need to know? The photoelectric equation is H times frequency is the work function plus 1/2 m of the electrons times V max squared. So H times the minimum frequency is equal to phi. Okay, now let's answer. Let me use a clean page. So one photon is absorbed by one electron, right? And in both cases, okay, the intensity of light is the same. Initially, layer 1 absorbs photons with a larger frequency. Photons that reach the second layer, oops, I hope you can read it. Okay, let me try. So, try with my handwriting. So photons that reach the second layer have a larger frequency than necessary for layer 2. For layer 2 to release electrons. Okay, if layer 1 is removed, the rate remains the same. Okay, since photons that used to be absorbed by layer 1 are now absorbed by layer 2. And that's the answer. I want to check the mark scheme just to make sure that I didn't mess up something. Okay, so this is part B. So the mark scheme says for 1 mark, the number of photons arriving each second on the cell is the same. Okay. Then second point, initially layer 1 absorbs photons with the greater frequency. And then the third point they mention is photons reaching layer 2 have an energy greater than the work function of layer 2. Okay, we said that. The other point they mention is that 1 photon interacts with 1 electron, and the last point is that so the rate at which electrons are released remains the same, just like we answered, and we are free to move on to part C. Okay, let me check. What did I do here? Okay. A student connected 2 solar cells in series with a 4 ohm resistor as shown. The student adjusted the light conditions so that each solar cell had an EMF of 5 volts and an internal resistance of 0.8 ohms. The power dissipated in the resistor was 13 watts. The student suggested that connecting the cells in parallel would cause the power dissipated in the resistor to be less than half this value. Deduce whether the student's suggestion is correct. Okay, so okay, let me replace this. Okay, I'm gonna use a clean page to replace I'm gonna replace this circuit with what they actually tell us. So we have two solar cells with the same internal resistance connected with this resistor of 4 ohms, and they give us the internal resistance as 0.8 ohms, and this voltage is 5 volts. Okay, so let's find the current in this circuit. So the conventional current goes this way. So we can just write that we have 5 volts. Oops. I'm getting tired. So 2 times 5, right? Because we have the two batteries. This is also 5 volts. Minus the current, let's call it I, okay? Minus the current times 2 times the internal resistance plus this guy, which we will call capital R, is 0, right? So the current, so we have 10 equals 5.6 I. So I is 1.79 amps. Okay. Okay. So let's now connect them in parallel. Let me use another clean page. Okay. So in the second investigation, they tell us that, okay, we still have this resistor. Okay, 4 ohms. But we now connect the solar cells that we will replace with batteries. We connect them in parallel. So this is the arrangement. Okay. Okay, so this is R, this is the battery, and this is the circuit. Okay, let me erase this. Okay, so this is the amp, this is the internal resistance. Oh, and I need to connect it over here, over there. So we have, for this part of the circuit, we have 1 over R total is 1 over R plus 1 over R. So R total is equal to the internal resistance over 2, or 0.4 ohms. Okay. Now R total is in series with the 4 ohm resistor. So R total, let's call it prime, is we have to just sum, so 4.4 ohms, right? Also, the current is now equal to the amp over the total resistance prime, and we just use 1 amp just because they are connected in parallel. So it's just it's like having just one battery when batteries are connected in parallel. Okay, so that's 5 over 4.4. So 1.14 amps is the new current, and P is I squared times the resistance dissipated in the 4 ohms resistor. So 1.14 squared times 4 yields, let me use my calculator, 1.14 times 4 is 4.56. Sorry, I squared times 4. I squared times 4 gives 5.2 watts, which is less of what it was before. So a short explanation why batteries in parallel do not add up is that okay, they have to be in series to be added up, but you can think of them as two, like let's say that you have a lake with water, and then you have another lake with the same water, the same height of water next to each other. Okay, so these can be thought of as two batteries in parallel. So the water flowing out of them will be the same. I mean, the flow rate will be the same. But if you add the two dams on top of each other, that's what batteries in series represent. Like you add the voltages. Okay, I hope this makes sense. And okay, this was I think this is it, right? Yes. Okay, this was Unit 2 from January 2024. I hope you like this video and that it is useful to you. Let me know what you think about these videos in the comments. Like and subscribe, and see you in the next video.